Far beyond our solar system, in the ghostly aftermath of stellar explosions, neutron stars silently bend the laws of the universe. They're small, only about the size of a city, but pack more mass than our entire sun. How is that even possible? If you held a teaspoon of a neutron star, it would weigh as much as a mountain, roughly 6 billion tons. But how can something so compact exist? To understand, we must begin where all massive stars end, the violent core of a supernova. When a giant star exhausts its nuclear fuel, gravity wins and the core collapses in a fraction of a second. In that terrible collapse, electrons and protons are crushed into neutrons. The star dies, but the dense core survives. What's left behind is no ordinary object. A neutron star is gravity's strange compromise between complete collapse and total destruction. In just 20 kilometers across, it holds more mass than 1.4 suns. So dense, atoms themselves are crushed beyond recognition. To grasp how strange this is, imagine compressing Mount Everest into a single sugar cube. That's the universe of neutron stars. Their gravity is so intense, anything nearing them accelerates to unimaginable speeds. Time, space, and matter no longer behave normally. Even light itself bends around neutron stars. They reveal themselves by tugging on reality in subtle, visible ways. Yet many neutron stars advertise their presence through their brilliant beams, pulsars, lighthouses flashing across galaxies. These pulsars spin with mind-bending speed, sometimes hundreds of times per second, faster than a blender, a bullet, or a jet engine. Imagine a star with the mass of the sun compressed into a 20-kilometer ball spinning 700 times per second. It exists. The fastest known pulsar spins 716 times each second. If it slowed down just slightly, it would collapse into a black hole. But what stops it from collapsing? The answer lies in neutron degeneracy pressure, a quantum force from the universe's weirdest rulebook. Unlike normal matter, neutrons obey Pauli's exclusion principle. They refuse to occupy the same quantum state, even under crushing force. This quantum rebellion balances gravity's urge to collapse the star into oblivion. For now, it holds. Yet there's a limit. Stack on just a bit more mass, and gravity overwhelms quantum resistance. The star becomes a black hole. That tipping point is called the Tolman-Oppenheimer-Volkoff limit, somewhere around 2.16 solar masses. Beyond it, no known force can hold back gravity. Before that final collapse, neutron stars display exotic behaviors. Some even vibrate in starquakes, cracking their hardened crusts. These starquakes shift the powerful magnetic fields wrapping the star, unleashing bursts of radiation across galaxies. Magnetars are the wildest neutron stars. With magnetic fields 1 trillion times stronger than Earth's, they twist physics into knots. A magnetar's field could erase your credit card, from halfway to the moon. That's pure electromagnetic insanity. Some neutron stars even merge, colliding in fantastic displays of gravity, light, and energy visible across the universe. These collisions create ripples in space-time, gravitational waves, first detected by LIGO in 2015, confirming Einstein's century-old prediction. The energy released in one merger momentarily outshines all the stars in the observable universe combined. But perhaps their most unexpected secret: neutron star collisions forge heavy elements like gold, platinum, and uranium. Your wedding ring, your smartphone, perhaps even your fillings, are fingerprints of long-dead neutron stars colliding in cosmic violence. The iron in your blood? Likely born from ancient supernovas. The gold on your finger? From merging neutron stars. Every atom heavier than iron required impossible violence to exist. Energy that only crashing neutron stars can provide. We owe our cosmic origins to these tiny, mysterious corpses drifting in space, dead stars, still shaping life. Yet for all we know, neutron stars hold secrets we cannot yet decode. Their interiors may hide exotic matter, unlike anything on Earth. Some theories propose a layer of quark matter, particles even smaller than neutrons, perhaps a soup of the universe's building blocks. Others imagine superfluid interiors, frictionless liquids spinning inside neutron stars like ghostly hurricanes of spacetime. These fluids may rotate separately and faster than the crust, causing mysterious glitches in pulsar timing still unexplained. Tracking these glitches gives insight into the mechanics of particles under pressure beyond imagination, in conditions we can't replicate. So why study neutron stars at all? Because they test physics at extremes nothing on Earth can replicate. They challenge every rulebook we've written, from gravity and magnetism to time and quantum behavior. New telescopes have let us see deeper than ever before, revealing neutron stars in X-rays, gamma rays, and radio pulses. NASA's NICER telescope on the ISS is mapping neutron stars in exquisite detail, revealing their size, temperature, and heartbeat. What it finds may rewrite our understanding of the nuclear force, the glue holding neutrons together inside atoms. We're even exploring how neutron stars behave near black holes when the two darkest forces in space collide. In 2020, we detected our first neutron star colliding with a black hole, an event that sent out light and gravity alike. Each new detection unlocks deeper insight into matter's limits, how dense, how strange, how enduring it can be. Scientists still debate the inner structure of neutron stars. What lies beneath that unthinkably hard crust? Their crust is thought to be the strongest material in the universe, 1 billion times stronger than steel. Yet even that strength is tested. Starquakes ripple through, release magnetism, and roll across the surface in firestorms. What could we learn by decoding these cryptic motions? Clues about matter tied more tightly than thought possible. In every way, neutron stars defy our everyday perceptions of size, mass, and physics.